difference in the ability of these liquids to flow. The ability of a liquid to resist flow is called viscosity. Water has a low viscosity because it flows freely, while substances like syrup and honey have a high viscosity because they flow very slowly. We can measure viscosity quantitatively by measuring the rate at which a metal ball falls through a substance. The slower it falls, the more viscous the liquid. There are a number of factors that dictate the viscosity of a liquid. First, we must look at the intermolecular forces occurring between the molecules. The greater the attraction between the molecules, the stickier and more viscous the liquid will be. The size and shape of the molecules also play a part. A liquid with very tiny molecules will be less viscous because of enhanced mobility. Very large molecules will have a more difficult time moving past one another, which will restrict flow and result in a greater viscosity. Lastly, there is temperature. Higher temperatures mean more kinetic energy, which causes the intermolecular forces to dissipate and will result in a reduced viscosity. So, a substance like water has a very low viscosity, despite the strong hydrogen bonding, because water molecules are so small. More complicated substances like honey will have much larger viscosities. Intermolecular forces also determine things called cohesive forces and adhesive forces. Intermolecular forces, whether dispersion or dipole-dipole, that are occurring between the molecules of a liquid are called cohesive forces. These are attractions that molecules can exhibit between one another that cause cohesion in a substance, which can be quite significant for a very viscous substance. In a liquid, these cohesive forces are felt equally in all directions by most of the molecules, but not for molecules that are at the surface of the liquid. These molecules only interact with half as many molecules as the others, because they are at the edge of the substance, with no more molecules to one side. This is why liquids tend to contract to form shapes that minimize their surface area. We can see this in a drop of water, which will be roughly spherical. The sphere is the shape that minimizes surface area, so a water droplet will adopt this shape to maximize the hydrogen bonding that is occurring in the droplet, allowing the system to sit at the lowest energy possible. Of course, if this droplet becomes larger, other effects like gravity and air resistance come into play, and it will not remain spherical for long. But in a tiny droplet, we can see this effect quite pronounced. The interactions between the molecules of a liquid and some solid surface are called adhesive forces. These describe the ability of a liquid to adhere to that surface. Take water, for example. If we place a drop of water on a piece of plastic or some other non-polar surface that won't interact with water, the water will not wet the surface, and it will retain a spherical shape. This is because the cohesive forces, the hydrogen bonds occurring between the polar molecules inside the droplet, are stronger than the adhesive forces between the water and the non-polar surface. But if we place a droplet on glass or another polar surface that will interact with water, it will spread out and maximize interactions with that surface, because in such a case, the adhesive forces are stronger. We can see this happening when we place liquids in a glass tube, like a graduated cylinder. Because water is attracted to the glass, it will form a concave meniscus, meaning that the surface will curve downwards. That is because this configuration will allow water to maximize its interactions with the sides of the glass tube. If we try this again with mercury, it will look totally different. In mercury, the cohesive forces between the mercury atoms are stronger than the adhesive forces between the mercury and the glass. So mercury will form a convex meniscus, which is when the surface curves up like this. It will do this so as to minimize interactions with the glass, which in turn maximizes the interactions between the mercury atoms. This is why the mercury in a thermometer is curved in this manner.